Okay. Ladies and gentlemen, we are busy with Chapter 4, Unsteady Heat Transfer or Transient Heat Transfer. And we already had, I think, about 6 lectures. I think this is lecture number 7. This chapter in Cengel and Ghajar is divided in a few parts. We are now busy with the second part. We have first looked at the lumped system approach. And now we are busy with a section on transient heat transfer in long plane wall cylinders and spheres. In the first section, the approach that was used was called the lumped system approach, and that system can be used or would give good results if the conduction resistance is about 10 times smaller than the convection resistance. It would mean that in general, in the body, there will be no temperature differences. All the temperatures would be about the same as they change as a function of time. Now, many bodies are not like that, okay? And therefore, we have to develop other tools to be able to solve it. And that we've done in this part of the paragraph on transient heat transfer in long plane walls, in long cylinders and spheres. Why the long and the long? To ensure that the heat transfer is only in one dimension. Okay, so there's no heat transfer at the top and at the bottom. We would say in terms of the area that it is negligible in comparison with the total heat transfer area where the heat transfer will occur. So for this special case, we've started with the energy equation, we've derived the equation. There were a process of non-dimensionalizing it, and the result were these equations. Aaron, if you can zoom in on it quickly for us, which is given in table 4.1 in your textbook. Those are then the analytical solutions for the plane wall, the cylinder, and the sphere. Theta, the non-dimensionalized temperature, defined here in the fine print as a function of lambdas, okay, and j's. Okay. And the lambdas can be determined from the Biot numbers. They are the roots of the value of the Biot number, and the Biot number is defined also in the fine print. With the lecture of yesterday, I've shown you how easy it is to make a mistake. If you've calculated a Biot number somewhere, you have to be very careful to use it somewhere else, because you always have to look from where it was derived. Okay. So in this case, with these derivations, we have to calculate the Biot number and the Fourier number as given here. And it all came out of the derivations. So that is where it comes from. Right. And we did an example yesterday. Today we're going to do another problem. Okay. And the problem that we're going to do is problem 459, the back of the textbook. Problem 459 in the textbook of Cengel and Ghajar. Okay. Okay, and this problem says the following. It says a 65 kilogram beef carcass, there it is, not there, there it is. So Aaron, if you can zoom on it quickly while I read the problem. So a 65 kilogram beef carcass, it's given the K value of 0.47, alpha is given, is initially at a uniform temperature of 37 degrees Celsius. It is to be cooled by refrigerated air at minus 10 degrees Celsius, flowing at a velocity of 1.2 meters per second. The average heat transfer coefficient between the carcass and the air is 22 watts per square meter degrees Celsius, and treating the carcass as a cylinder of a diameter 24 centimeters and height 1.4 meters, and disregarding the heat transfer from the base and the top surface, which means that we can consider it as a one-dimensional problem. Determine how long it will take before the center temperature of the carcass would drop to 4 degrees Celsius. Okay. So Normally in these types of processes it is very important to cool the carcass down, but not to freeze it. Okay, so they wanted to typically a temperature of 4 degrees Celsius, but then they also ask, also determine if any part of the carcass will freeze during the process. Okay. So will there be somewhere, some of the meat, will the temperature drop to 0 or lower than 0? And then I'm going to add a few more sections. You don't have to write it down now, I'm going to do it in detail. Then I'm also going to add to this problem, determine the amount of heat transfer, then the average heat transfer rate, and then determine the energy consumption and the cost for this system, which is a refrigeration system. Normally you use a vapor compression system. You've done it in thermodynamics. You remember something about the COP of the system, how much heat you can remove in comparison with what you pay for, which is determined by the compressor. And let's assume a COP of 2, which would be very typical for a system like that. And let's assume a cost of 2 Rand per kilowatt hour. What will the cost be of this process? So that is the last part of the question. Right. So let's just make the problem so that it is a little bit more schematic and easy for us to work with. That's the carcass, which we now say can be considered as a cylinder. Okay. And it has a diameter of 240 millimeters and a height of 1.4 meters. Okay. The initial temperature must be 37 degrees Celsius, okay, approximately. The mass is given as 65 kilograms. Okay. The K value is 0.47 watts per meter Kelvin or degrees Celsius. The alpha is equal to 0.13 multiplied by 10 to the minus 6 square meters per second. And then the last thing, which is not given here, but we will need that, is the CP value. And let's assume a CP value of about water, which is about 4,180 joules per kilogram degrees Celsius. Okay. So that is the property of the carcass. Okay, the cylinder, a cylinder of meat in principle now. Okay. Right. On the outside, we have a refrigerated air at a temperature of minus 10 degrees Celsius. Okay. A velocity of 1.2 meters per second for the air. Okay. And the heat transfer coefficient of about 22 watts per square meter degrees Celsius. Okay. So that is the most important properties of this problem. Initially at 37 degrees Celsius, the mass, the K value, the alpha value, CP value given, the diameter and the height. On the outside, the temperature at T equals 0, it's now minus 10 degrees Celsius. The velocity of the air is 1.2 and the heat transfer coefficient is 22. Right. Now, determine the following. We determine firstly the time for the carcass to drop to 4 degrees Celsius at the center. So the time for the center temperature, okay, remember the center T0 indicates at the center or where R is equal to 0. Okay, so how long will it take for the center temperature to drop to 4 degrees Celsius? Okay. Then the next part is, will any part freeze? Okay. Will any part of the carcass freeze? Then, in addition to this problem, the amount of heat transfer. HT, heat transfer, okay? The amount of heat transfer. Then the average heat transfer rate. The first one, the amount of heat transfer. The second part, the average heat transfer rate. And then the energy consumption with a refrigeration system with a COP of 2, okay, an electricity tariff of R2 per kilowatt hour. $65 kilogram beef carcass, K value is given, alpha given, etc. Initially at a temperature of 37, to be cooled by refrigerated air, -10, flowing at a velocity of 1.2 meters per second. Average heat transfer coefficient 22, treating the carcass as a cylinder, diameter and length given, disregarding the heat transfer from the base and the top. So we say there's no heat transfer from that surface and no heat transfer from that surface. Okay? Obviously an assumption so that we can make sure we've got one-dimensional heat transfer. Determine how long it will take for the center temperature to drop to 4 degrees Celsius. Also determine if any part of the carcass will freeze during the process. Then, in addition, the amount of heat transfer, the average heat transfer rate, and the energy consumption with a refrigeration system COP of 2 and at a cost of R2 per kilowatt hour. Ladies and gentlemen, do you understand the problem? Are you all with me and can we start, or are you still writing? You all ready? Good. Okay. So, all the mathematics has been summarized for us neatly in table 4.1. Okay. It gives us the solution for a plane wall, a cylinder, and a sphere. The non-dimensionalized temperature with a long mathematical equation. It looks very complicated. Remember, again, I've told you previously, remember that 5 should be an equal sign. It's a printing error in the textbook. Okay. Now, we are in this case working with a cylinder. So, although there are other equations in the textbook, I want to start here and I want to show you in very simple steps, how did we previously get to the other equations? Because sometimes it's a little bit confusing how these things relate with each other. Okay, so specifically, if we now look at table 4.1, okay, specifically the cylinder, then for a cylinder, the non-dimensionalized temperature is n equal 1 to infinite, multiplied by 2 times lambda n, multiplied by J1 divided by J0 square of lambda n plus J1 square multiplied by lambda n. Okay, so that term multiplied by e to the minus lambda n square tau multiplied again by J0 lambda n multiplied by r divided by r0. Okay, so I'm writing this just a little bit different. Okay, in principle, that's the equation. Okay, now if you look at that equation, it looks very complicated and confuses many students, especially now when you look at this stuff and you look at this lambdas and J0s and J1s. So, now together with that, that actually makes it more complicated is the fact that next to it, it now gives us the roots. And these roots, in this case, is lambda n multiplied by Jn in lambda n divided by J0. Lambda n is equal to the Biot number. Now, at least we can get the Biot number. Okay, so the Biot number, fortunately that is very simple to calculate, is equal to HR0 divided by K. Where do we get it? Here in the fine print, Aaron, if you can just zoom in for me, the Biot number is equal to HL divided by K, or H0 divided by K, okay, for the cylinder and the sphere. So that is where it comes from. The heat transfer coefficient is equal to 22. The diameter is equal to 0.120 divided by the thermal conductivity, which is equal to 0.47. And the result is a Biot number of 5.62. Okay, so most students can sort of look at this equation and they say, well, at least I can calculate the Biot number very easily. But now they start becoming very anxious, because now they look at this equation. Because obviously, you need to get the solution of that to get the lambda values, which looks very complicated, and maybe it is a little bit, because at the end, those are functions just like a sinus and cosine or whatever, and you need to get it somewhere, or you have to solve it yourself. Now, so when students see this, they say, you know, help. Now, fortunately, in table 4.2, so if we look in table 4.2, okay. So in table 4.2, if I can enlarge that a little bit for you, something like that, then some of these values are given. But it is important to remember it's not all of them. So you need to understand that the solution of theta, okay, is actually equal to the case where n is equal to 1, and then you have to get all the roots and do the calculation, and then you have to do it for n equal to 2, etc. Okay, so this would be for n equal 1, that would be for n equal 2, and that would be for n equal 3. And for each one of them, we need a constant, and everything in here, all that, is A(n). Okay. So that is the constant A. Okay. So for n equal 1, it would be A1, okay, multiplied by e to the minus lambda 1 tau, okay, multiplied by J0 lambda 1 multiplied by r divided by r0. That would be the first term. Okay. The second term would obviously be plus A2 e to the minus lambda 2 tau multiplied by J0 lambda 2 r divided by r0. Okay. So that would be A2, that would be lambda 2, and that would be lambda 2. Okay. And the third one, the same, A3 e to the minus lambda 3 tau J0 multiplied by lambda 3 multiplied by r divided by r0, etc. So, in table 4.2 is the result of n equal 1 only. It doesn't give us the results for n equal to 2, 3, etc. thus. So if we look in the textbook in table 4.2, for the Biot number, okay, don't make the mistake to use the first two, because remember the first two is for the plain wall, the next two is for the cylinder, and the two after that for the sphere. Many students in the test and exam, because they are so anxious and in such a hurry, normally use the first two. Okay, so be careful for that. Use the right ones. Okay, so the Biot number is given for the plain wall, and then the Biot, or the results are given for the cylinder. Right. Now, at a Biot number of 5, the results are given for lambda 1 and for A1. And take note, it is only for the first roots of lambda 1 and the first value of A1. Okay. So at 5, the result lambda 1 is equal to 1.9898 and A1 is equal to 1.5029. Okay, you can try to check that for me. So those two values there, the Biot number of 5, 1.9898 and 1.5029. You agree? Okay. We need the values at 5.62, which is now unfortunately between the two. So at a lambda at the value of 6, Biot number of 6, then the values is 2.0490 and 1.5253. In your study guide, I've given you some information on corrections that needs to be done. Okay, but we will get to that later. Right. So those are the lambda values and the A1 values. Okay. But we need it for 5.62 in between. And if you go and do the interpolation, then the value would be equal to 2.027 and 1.517. Okay. Yep.
Sorry, so for your pizza at the top, under your table 4.2, you said that A1e to the power of negative lambda 1 tau. Is it not lambda 1 squared?
Yep, sorry. Okay, lambda 1 square, lambda 1 square, lambda 1 square. Yeah. Yep. Okay. Right, so now we've got lambda 1 and A1. And remember, it's now only these two values. It's for the first term only. So doing it for the rest is quite a mess, okay, and a lot of work. So usually you have to hope that you can get away with a first term approximation. And that is when tau is larger than 0.2. So what we're going to do is, because we don't know what tau is, because they ask us the time, okay, and tau is the non-dimensionalized time, so we don't have that yet. So we're going to make the assumption that tau is larger than 0.2, so that we can only use the first term. So before we get there, let's just go back a little bit. Okay. Then, let's do that. Okay, assume tau is larger than 0.2. Why? Because then the one term approximation would be valid. So if we now look at theta, we would say that the non-dimensionalized temperature is equal to the first term only, which is equal to theta 1, and theta 1 is equal to A1e to the minus lambda 1 square multiplied by tau multiplied by J0 multiplied by lambda 1 multiplied by R divided by R0. And let's call that equation 1 because we're going to use that equation a little bit later. Okay, so the one-term approximation, but that is now what we will have to go and calculate. But if we look at this problem, they want us to determine the temperature at the center. Okay, at the center. Now, if we look at this equation, what happens at the center? At the center, R is equal to 0. Okay, you agree? Okay, which then means that J0, this part, must be J0 of 0. Okay, the first Bessel function. Okay, let me see if I can get that quickly for you. Right. Table 4.3. Okay, so in table 4.3, we need J0 at 0. Okay. Now that eta, many students are being confused by eta. What is eta? Where does eta now come from? So that would be obviously, we are interested for the case where eta is equal to 0. So that is the value of eta. Okay. So if we now look at eta for J0, what would that term be equal to? Okay. So we see that term is equal to 1. You agree? Ladies and gentlemen, you happy with it? You with me? So this equation means now the special case of theta at 0. The temperature at 0 would then be equal to A1 e to the minus lambda 1 square multiplied by tau multiplied by 1, if you want to put in the J0 value there. Okay, so this is at R equals 0 at the center. This theta 0, what does it mean? It is nothing less than the temperature, the non-dimensionalized temperature, which has been written in the following format. And again, we just look at table 4.1, and there it is given in the fine print. The non-dimensionalized temperature is the temperature minus T infinite divided by Ti minus T infinite. Okay? So we can, in many cases in this course, we just write it like that. Temperature at 0, okay, minus T infinite divided by Ti minus T infinite is equal to A1 e to the minus lambda 1 square multiplied by tau. So that would be the equation that gives us the temperature at the center. That is why it looks different than the equation in the table. There's just 2 or 3 steps to use the equation from the table to derive the temperature at the center. Okay, so there it is. So now let's go and calculate what we want to calculate. Okay. We want to know when will the temperature at the center be 4 degrees Celsius. That is the question. Okay. If we go back to this, okay. In terms of what was given, Carcass was at 37, outside minus 10. Now they want to know how long will it take before the center temperature is 4 degrees Celsius. So that temperature is 4 minus 10. Okay, the outside temperature divided by the initial temperature, which is 37, again minus the outside temperature, which is minus 10. Okay. And that is then equal to A1, and A1 is equal to, from that table, okay, 1.517 multiplied by E to the lambda minus lambda, and there's the lambda for us, the first term of the root, minus 2.027 square multiplied by the non-dimensionalized time. The only unknown is the non-dimensionalized time. Okay, so we can calculate that as 0.396. Okay. And what do we say about this? Okay. We were fortunate, okay, so because we've assumed tau is larger than 0.2, and indeed it is larger than 0.2, so the approach that we've chosen of only using the first term is valid. Yep.
If it isn't valid, how would you get numbers to where do you get that?
Yes, okay, a very good question. If that is not the case, where do you get the other values? First answer, it's not in the textbook. Okay, so in the test and exam, you will just have the textbook, so I will not expect of you to go and get the other ones or to solve it. So I will limit myself to the textbook and what is available in the textbook. That's the first answer to your question. But getting the other roots are very easy. I've referred you to, in the beginning of, at the back of the first page of your textbook, there's a CD in with a software called EASE. Okay, and that EASE can solve all those roots for you very easily. Or this morning, I did a quick Google, and there was a website that can give you all these values up to 22 digits. Okay, very easily, and I will post that on the announcement so that you can get it. So it is available, but at the same time, it is an important question because I'm going to show later to you that there are actually errors in the textbook in the table. Okay, and I've picked it up this morning with some of the J values, or I will show you later, and so just take note of it, and it is very important. So it is available, but not in your textbook. Okay, right. So the non-dimensionalized time is equal to 0.396. The non-dimensionalized time is equal to alpha t divided by R0 square. Where do I get it? Where does this come from? Again, refer to table 4.1. There tau is defined for a plane wall and for the cylinder and the sphere. Okay. So that is equal to 0.396 is equal to alpha, which is equal to 0.13 multiplied by 10 to the minus 6, multiplied by the time in seconds that we want, divided by the radius, which is equal to 0.12 or 120 millimeters square. And from that, we can solve the time as 43,865 seconds. It's not the type of an answer that an engineer would give. Okay, it doesn't make sense to me. So that would be 12.2 hours. Okay, 12.2 hours, that is how long it will take. Any questions? Are you with me?